back. For the last 13 years, a U of I professor and team of researchers have tried establishing better technology for spacecraft. Spinning disks typically help it rotate, but they say reliability and vibrations can cause problems. Missions have failed because of it, and now there's an interest in alternative tech to avoid that from happening. The work is paying off, and a company in San Francisco is taking interest. WCIA 3's Amanda Brennan brings us inside an engineer's lab.
So this started as a collaboration with JPL quite a while ago in 2013, and they had a challenge that was really interesting to me. I'm a design research person. I study methods for helping engineers do a better job of designing complicated engineering systems. And in talking to some of the engineers at JPL, I felt like some of the design methods my group studied, they could have an impact on design of spacecraft attitude control systems. So this was the first prototype, a relatively simple prototype that helped us to give a proof of concept. But it started out really just as initially trying to help a spacecraft to not vibrate very much. So when we were applying some of the design methods that have been developed by my research group, in the process of that, we made it really a breakthrough discovery that allowed us not only to cancel out vibrations in spacecraft, but use the same system with what are called piezoelectric actuators, this material that can expand or contract when you apply voltage to it, to not only cancel out vibration, but also to rotate the spacecraft itself. Most spacecraft need the ability to rotate themselves in a desired direction. So this could be for things like space telescopes, where maybe we're looking for exoplanets and we need to point very precisely, or maybe they're for satellites that are pointing back at Earth, taking images of Earth. They need to point very precisely as well. And the basic idea is these actuators can both push and pull these panels that represent solar arrays. So we can either twist them to the right or to the left, or we can extend them out and pull them in with those actuators. So with that capability, we could go through a specific pattern of motion that then allows the spacecraft to rotate to a desired position. But this is not the type of actuator that is ending up on the real spacecraft, but it at least demonstrated, it proved that this concept actually worked in real life. This is the next evolution of the same concept. So once we had this prototype complete and tested, then we moved on to using different types of actuators. Special smart material, where if you apply voltage on the top and the bottom, it can expand or contract depending on how you apply voltage to it. These were used in some of our prototype tests. The PCBs have these long slots. They work as a flexible or compliant mechanism, so there are no moving hinges, no pin joints. But then the piezoelectric actuator is this tiny little piece right there, and that allows us to extend or bend the PCBs that represent the solar panels that would be on the spacecraft. So those were successfully tested using the air bearing setups that we have over here, both using a spherical air bearing and also a single degree of freedom air bearing, or that allows spacecraft to rotate just about a single axis. When we have the real system working, especially those with the piezoelectric actuators, it's really difficult to see what's going on. These are things that are moving really quickly and moving by just very small amounts, very small displacement. We go through the same patterns of motion, but at a more human scale. Slow things down and use bigger movements, then we can see more what's going on. The platform here, this basically heavy-duty Lazy Susan, it reduces friction. It's not friction-free, but I can go through a pattern of motion that mimics what we're doing with MSAC. So if my arms represent solar arrays, and then I twist my arms, my body twists the opposite direction. But if I twist back with conservation of angular momentum, then my body just goes back to the original position. This is really the basis for a lot of different things that either gymnasts or cats can do. So a cat falling out of the window uses the same basic idea so that it can rotate itself in midair and land on its feet. It will be used in space very soon. So we have a spin-off company that was started by a group of University of Illinois alum. Fairly recently, they delivered their spacecraft to a company that's going to launch it in 2026. And then they have plans for their first commercial scale large spacecraft that they're going to launch using MSAC technology that should be launched in 2027. It's really satisfying. Not everything pans out in academic research, but sometimes we have what some might call the long arc of success. We make some early investments, there might be a lot of risk, we don't know if something's going to pan out, but some of them do, and it can make a big difference, not just for technology, but all of society.
That's Amanda Brennan reporting. Our space coverage doesn't end here. They're going to be launching later this week, and you can catch that liftoff on the morning show on Wednesday at 6:30 a.m.